Now, that's for hemisphere. But if you were to have a conductor, we'll read like this. The length is L. Then the formula will be like this. Okay, it depends on the current, how the current flow, but this formula usually we use. The resistance of electrode vertical is given by rho over 2 pi L ln AL over D. D is the diameter minus 1. Okay, so this is the formula for that resistance of a vertical rod. Do you know what is the resistance if you make the rod horizontal? You know? Okay, if it's horizontal, I think the formula is at the fourth one there. Horizontal strip. No, the third one. Okay, and so on. So you can see this is the, this is for vertical, this is for horizontal. All right. If you have two vertical like this, then the formula becomes like this. It depends on your S and L. Straight means like this. Your it's not horizontal. It's not a conductor cylindrical. It's like a tape with, is it, or something like this. All right. So you have many formula here. You can just put a star, 4-point star, 6-point star, a ring, horizontal round plate, and so on. Vertical round plate. Horizontal means the plate is horizontally aligned. Vertical means it's vertically aligned in the soil. So you have the whole range of formula. This one you just derive, and the rest. Okay. Now, you can see more formula here. I think you can see here, if you have two rods in parallel, which one has more resistance? The single one or the double one?
Single one.
Okay, single is larger than R2. Correct? Okay, the formula we prove it, but you must think about the distance. Okay, usually you should make it much bigger, the spacing, so that is efficient. Okay, but if you put two in parallel or three in parallel, doesn't mean that your resistance reduced by 3. Okay, it's not as efficient as normal resistance. Okay, it says here. Huh? So you must. Okay. But if you put a grid, I think there is an equation for the grid. Anyone see a grid? No, it's not here. Okay, grid means like this. Inside the soil. Okay, it's like a mesh inside the soil. Then the formula is, so this is usually done for substation. Okay, there's a formula for that. But one equation is given here. like this. Okay, given here the equation, example of equation. It depends on the grid length and so on, some factors. So when you design a substation grounding, you want the grid resistance R to be as low as possible so that you have safe touch and step potential. You have safe step potential. So you need to reduce and reduce R until you have safe touch and step potential. So until you get the value, you don't stop designing. So you just change L here, the amount of conductor, until your touch potential or step potential is acceptable. Understand? What I just said just now is actually over 200 pages standard. I just say in one sentence. So the design is actually for substation is to make sure enough conductors inside the grid, enough conductor here, total conductor is L, and there's some other spacing factors and so on. So you must increase L and your reduced resistance is reduced so that your step potential is smaller, acceptable. Acceptable. E and charge is acceptable. Acceptable means they are lower than the tolerable one. So this thing is the whole design of grounding substation. You understand? You increase L or the amount of conductor or the grid configuration until resistance is low enough to give you low enough E touch and E step. Okay, I'm going to skip the impulse. I've already mentioned to you just now the equivalent step. As I said, there are two parts that is important inside this chapter, the second part and the last part. So I'm going to skip this one because this is already earthing system design. And I said just now, I just summarize in this short notes here. So the design is here in this page. See? This part. This is the design, the concept of the design. Now, you can look in detail for that one, whether it's substation or whether it is a tower. So these are the detail of the substation design. The L just now, or sorry, the touch. This is touch or step. This is the conductor size to give you acceptable, because T there is the time, tolerable time. 76 is I think the weight. Maximum temperature rise at ambient temperature, and so on. Okay, this is A. A is the conductor size, cross section, and this is formula for E step. Acceptable. So you need to design until E step is smaller than that. We give you KS. E step again here. And then E touch. This is acceptable. Okay, and you equate this. This is from your design, and this is tolerable. This is, we give you the design L. Okay, same for gas insulated substation and tower resistance. You can read this later on. Huh? Okay, if you want to apply the grounding, you can see many types here: stranded, solid, coated, uncoated, in concrete, in soil, in open air. So all these are design standards. And how can you increase or decrease the resistance inside the soil. Okay, just read this one for your information. In this page, give you some criteria for good earthing. Okay. Why you need a good earthing? For protection, for safety, to reduce EMC, and for your power quality. Because if you have high earthing, sometimes you cannot give safe. Circuit breaker can be influenced by grounding. Grounding as well as lightning may be sometimes just a single earthing. It has to be bonded together, forming one system. Okay, when you design, if you don't have any information about rho, you can use this. Rho equal to 100 ohm meter. Okay, this is a table again for your resistivity. Now this is correct one, ohm meter. Yeah, I think previously is correct. The previous table is correct because it's ohm centimeter. So ohm meter, 1 ohm meter is equal to 100 ohm centimeter. So you have to multiply this by 100 to give you, previous table you have large value. Now for clay, just now 500, now 50. So this is correct. 200. Okay. So the previous table also correct. Is ohm centimeter. Already done this one.